Greeting guys, so welcome back. So in this tutorial we'll be exploring VLM architectures. Like with the emergence of multimodal AI, we are seeing a revolution where AI can comprehend various modalities like text, image, speech, facial expression, psychological gestures. So the ability to process multiple modalities has opened up various avenues for AI applications. So one exciting application of multimodal AI is vision language model. So these models can process and understand the modalities of language, which is text, and vision, which is image, simultaneously to perform advanced vision language tasks like visual question answering, image captioning, and text to image search. So what is vision language models? So vision language model is a fusion of like vision and natural language models. It ingests the images and the respective textual description as input and learns to associate the knowledge from the two modalities. The vision part of the model captures the spatial features from the image, while the language model encodes the information from the text. So the data from both modalities, including detected objects, the spatial layout of the image, and text embeddings, are mapped to each other. For example, if the image contains a bird, so the model will learn to associate it with a similar keyword in the text description. So this way the model can learn to understand the images and transforms the knowledge into natural language, in text and vice versa. So let's look at some VLM architecture on the learning techniques that mainstream model like Clip, Flamingo, VisualBerts are using. So let's start with contrastive learning. So it's a technique that learns data points by understanding their differences. The method computes a similarity score between the data instances and aim to minimize the contrastive loss. So it's most useful in semi-supervised learning, where only a few labeled samples guide the optimization process to label unseen data points. For example, one way to understand what a cat looked like is to compare it with similar cat images and a dog images. Contrastive learnings models learn to distinguish between a cat and a dog by identifying the features like facial structure, body size, fur. So the model can determine which image is closer to the original and predict its class. So notable model which comes under this architecture is CLIP, as you see here. So CLIP is an example of model that uses contrastive learning by computing the similarity between the text and image embeddings using textual and visual encoders. It follows a three-step process to enable the zero-shot prediction. One is train a text and image encoders during pre-training to learn the image text pairs. Second is converting the dataset classes into captions and then estimating the best caption for the given input image for zero-shot prediction. The second architecture we're going to see is prefix language modeling. It is an NLP learning technique mostly used for like model pre-training. It inputs a part of text, a prefix, and learns to predict the next word in the sequence. So in visual language models, PrefixLM, which enables the model to predict the next sequence of words based on the image and its respective prefix text. So it leverages a vision transformer that divides an image into a one-dimensional patch sequence, each representing a local image region. Then the model applies the convolution or linear projection over the processed patches to generate contextualized visual embeddings. So for text modalities, the model converts the text prefix relative to the patch into a token embedding. The transformers encoder decoder blocks which receives both visual and token embeddings. The model learns the relationship between the embeddings. Popular architecture is SimVLM, which is using the PrefixLM learning methodology. It has a simple transformer architecture with just surpassing the results in various benchmarks. So it uses a transformer encoder to learn image prefix pass and a transformer decoder to generate an output sequence. The model also demonstrates good generalization and zero-shot learning capabilities. Similarly, if you see ViTs, it uses a convolution neural network to extract the image features and textual heads with the transformers to manage the text prefixes. You can train the model end to end to predict the correct image captions by feeding image text pass to the textual head. So moving on to our next architecture, which is frozen prefix language modeling. While PrefixLM techniques require training visual and textual encoders from scratch, frozen PrefixLM, which allows you to use pre-trained networks and only updates the parameters of the image encoders. For instance, the architecture you see here, which shows how frozen works using pre-trained language model and visual encoders. The text encoders can belong to any large language models, and the visual encoders can also be a pre-trained visual foundation model. You can fine-tune the image encoders so its image representation aligns with textual embeddings, which allowing the model to make better prediction. And another notable architecture is Flamingo. It uses the more state-of-art SOTA approach. It uses a clip-like vision encoders and an LLM called Chinchilla. Keeping the LLM fixed lets you train the visual encoders on images interleaved between text. So the visual encoders process the image through a perceiver sampler. The technique which results in faster inference and makes Flamingo ideal for few-shot learning. So moving on to our next architecture, which is Multimodal Fusion with cross-attention. So this method uses the encoders of a pre-trained LLM for visual representation learning by adding the cross-attention layers. So VisualGPT is primary example that allows quick adaptation of an LLM's pre-trained encoder weights for visual tasks. So as you see here. So we have to extract the relevant objects from an image and feed them to the visual encoder. The resulting visual representation are then fed to the decoder and initialized with weights according to the pre-trained LLM. The decoder module balances the visual and textual information through a SRAU. So SRAU is a method which avoids the issue of vanishing gradients, a common problem in deep learning, where model weights fail to update due to small gradients. So VisualGPT outperforms several baseline models like plain transformer, attention on attention, which is AOE transformers, and also X transformers. So moving on to our next architecture, which is masked language model, which is MLM, and image text matching, which is ITM. So MLM works in language models like BERT by masking or hiding a portion of a textual sequence and training the model to predict the missing text. So ITM involves predicting whether sentence Y follows the sentence X. So as you see here, you can adopt the MLM and ITM techniques for visual tasks. So this architecture, which is you're saying, just illustrate the visual BERT's architecture, which is trained on the COCO dataset. It augments the MLM procedure by introducing image sequences and masked textual description based on visual embeddings. The objective is to predict the missing text. Similarly, ITM predicts whether or not a caption matches the image. So moving on to the next architecture, which is no training. So you can directly use large-scale pre-trained vision language models without any fine-tuning. For example, Magic and ASIF are like training free frameworks that aims to like predict text description that aligns closely with the input images. So Magic, which uses a specialized score based on clip-generated image embeddings to guide the language model's output. So using this score, an LLM generates textual embeddings that aligns closely with the image semantics, enabling the model to like perform multimodal task in zero-shot manner. In the other hand, like ASIF, which uses the idea that similar images have similar captions. So the model computes the similarity between the training dataset's query and candidate images. Next, it compares the query image embeddings with the text embeddings of the corresponding candidate image. Then it predicts the description whose embeddings are the most similar to those of the query image, resulting in like comparable zero-shot performance to models like Clip and Lit. So if you see here, it just shows the prediction strategy as if it's using. So moving on to our final architecture, which is knowledge distillation. So it's a technique, okay, which involves like transferring the knowledge from a large, well-trained teacher model to a lighter student model with few parameters. So this methodology allows researchers to like train VLMs from larger pre-trained models. For instance, ViLD is a popular VLM which is developed using a knowledge distillation methodology. So the model uses a pre-trained open vocabulary image classification model as the teacher to train a two-stage detector, which is student model. So the model matches the textual embeddings from a textual encoders with image embeddings. Knowledge distillation transfers the knowledge from the image encoders to the backbone model to generate the regional embeddings automatically. So only the backbone model which generates the regional embeddings during the inference, and it matches them with the unseen textual embeddings. The objective is to like draw correct bounding boxes around the objects in the image based on the textual description. So that's it, guys. We are at the end of the session. So in this session, we just saw what is vision language models and how different architecture of VLM works, and what are the notable VLMs which uses these architecture. And finally, vision language model is like evolving field with great promise for like a industry. So like vision language models are a multimodal architecture that simultaneously comprehend image and text data modalities. These models which uses computer vision and NLP models to correlate the information like embeddings from the two modalities, and several VLM architecture which exists that aims to like relate the visual semantics to textual representations. So VLM can have like many industrial use cases like robotics, medical diagnosis, chatbots, and many other use cases. By understanding these foundational aspects, we can apply the VLMs across various industries, healthcare, robotics, and media to like create a more sophisticated and context-aware AI system. I hope you find this session helpful. So please let me know your queries in the comment section below. See you all in our next session. And until then, this is Abonia. Thanks for watching.